Let me now provide some additional motivation to the definition of an integral that is about to follow. And for that, again, we're going to look at the example of f of x equal to x squared, and I'm going to consider it on the interval from 0 to a for some real number a, some positive number a. As we discussed last time, right, the way to approximate an integral is to consider a partition of your interval into a number of subintervals, and then above each subinterval you construct a rectangle, and then in that way you approximate the area under the graph by adding up areas of rectangles. And then in order to figure out the exact area, you need to take a limit as the number of these subintervals goes to infinity. And we discussed that it's not really that easy to define what exactly we mean by the limit here, because, well, first of all, the number of intervals going to infinity clearly is not enough, because it is possible that the number of intervals goes to infinity, and yet maybe, say, this interval from x3 to x4 stays fixed. So I have a larger and larger number of intervals, so that area is approximated on some intervals better and better. On other intervals, it's not going to be approximated better. Maybe it is approximated worse if, for example, the interval from x3 to x4 is allowed to elongate. So actually, it's not that we need a number of intervals go to infinity, but we need the length of each subinterval go to 0. Right? Because in that case, by setting lengths of intervals to 0, you achieve a higher degree of accuracy. Then there is another question, on the other hand, is that on each of these intervals, when you replace the area under the graph but the area of the corresponding rectangle, you're making an error. And who says that if I consider more rectangles, then on each rectangle I have a smaller error, but how can I guarantee that when I add up errors from all rectangles, I'm going to get a decreasing number, a number that decreases as I make number of subintervals larger and larger. And a third overall, so when I'm trying to take a limit as lengths of each subinterval, of all subintervals go to 0 at the same time, then it's not really clear what I mean by this limit, because it's not a limit of a sequence per se, and it's not a limit of a function. So we have not discussed limits in this sense at all. So we have to search for a definition that would somehow fit within the developments that happened in this class prior to this point. And so in order to get there, let me look a bit more at this example, and I pre-drawn something here just to save time. So consider a function x squared on the interval from 0 to x. So I'm plotting exactly the same graph both here and here, and the only difference between the graphs that I'm going to consider will be in number of these subintervals. So if I take a set of points that I use to produce subintervals, on the left graph it would be 0, x1, x2, etc., and then a equal to x5. So in this case, I'm looking at 5 points. I'm going to call this 5 points a partition. So P is going to be a partition of the interval from 0 to a. Now, let me immediately consider two partitions. So in addition to P, I'm going to consider Q. So Q differs from P by the fact that all points are exactly the same in P and Q except for one point x star, which is going to lie between x4 and x5. So now the second partition is Q. Q has all the points of P plus one more. So then as a set, P is a subset of Q, proper subset because Q has one more point. In this case, we're going to call P refinement of Q, right? So if I have a partition P, Q is strictly a finite partition because it contains all points of P plus an extra point. If Q had extra 7 points, if it did contain all points from P plus an extra 7 points, then Q is still a refinement of P. And we'll talk about that a lot in the future. So I'm going to consider following approximations of the area then. So last time we said that when I design a partition like this, then in addition to prescribing subintervals on x-axis, I have to prescribe heights of rectangles that I'm going to use. And in principle, we saw that you can specify a blue point inside the interval, let's say from x0 to x1, and use the value of the function at that point, which I called x1 star, as a point where I would compute the height of a rectangle. But in this case, I'm not going to look at the interior points. On each interval, I would want to use the largest possible area supported by this interval. So, for instance, on the interval from x0 to x1, what is the largest possible height that I can use there? My function x squared is increasing, so the value at x1 is the largest. So f of x1 is the largest. So then if I use f of x1 as the height, then the height of a rectangle equal to f of x1 is going to be, which is x1 squared in this case, is going to be the largest possible area of the first rectangle. Likewise, x2 on the interval from x1 to x2, x2 squared is going to be the largest height, etc. And so then if I add up all areas of intervals in this left example, then I'm going to end up with an expression like this, right? x1 squared is the height of a first rectangle, x2 squared is the height of a second rectangle, x1 minus x0 is the base of the first rectangle, x2 minus x1 is the base of a second rectangle, and so on. So this is an approximation of the area, but in this case, clearly, because my function is increasing, right? So at each right-hand point, it is going to have the largest possible value in a given interval. Then that means if I use, like I'm using here, right-hand point of each subinterval as a point where I'm calculating the height of a rectangle, then I'm going to overestimate the value of the integral, right? And that's sort of the largest possible overestimation of the value of the integral or of the area under the graph by using this partition, right? So again, for a monotonically increasing function, the largest overestimation of the area on each subinterval that I can do is by taking as a height the value of the function at the right endpoint. Okay, so that's for P. Now what happens for Q? So for Q I'll use exactly the same idea. So again, for Q I have, if I use red rectangles, and I'm going to overestimate the area of under the graph on the interval from 0 to a. But if we just compare the pictures, right, overestimation here is going to be the sum of areas of these triangles that lie above the graph f of x equal to x squared. So on the right picture, I see exactly the same overestimations, except for on the last interval here. Now I'm splitting this interval into two, and I'm replacing then, because my function is increasing, on a half of this interval, I'm replacing a larger value with a smaller value. So then on the right, I still have an overestimation of my area under the graph, but that overestimation is smaller than overestimation by using the partition on the right. So if Q is a finer partition, then we sort of can conclude from that on a finer partition, overestimation is going to be smaller than overestimation on the partition before the refinement, right? More points, adding more points will decrease overestimation further, right? And so it kind of looks like that if I consider all possible overestimations by using partitions like this, all the overestimations are going to be going to have strictly larger area than the area under the graph. If you define the partition, then the overestimation goes down. If you refine it any further, it still goes down. So then if you think about it, I should be able to, so overestimations of the area under the graph by default are going to be bounded from below by that area under the graph. So that means that if I compute the infimum of these overestimations, hopefully that infimum is going to coincide with the area itself. Right? So once again, each time I use a right endpoint for x squared, I'm going to overestimate my integral. If I add additional partition points, then the overestimation will go down. So approximation becomes more exact. And adding more points will push it down further. All overestimations are bounded from below by the actual area under the graph. And so then it seems that if I take the infimum over all possible overestimations, that I should get my area. So in this case, I'll have to take infimum of all possible overestimations, and infimum we do know how to take, right? Because it's just an infimum of a set of numbers. Each approximation is a number, infimum of numbers. I understand what this means. So I can then compute the area without talking about the limit, right? I'm just considering all possible overestimations, and I'm finding their greatest lower bound. Yes. Mm-hmm. All right. So what about if we use left endpoints? So let's take same partition P, but now instead of using right endpoint of each subinterval to find the approximation to find the height of a corresponding rectangle, let's use a left endpoint. And again, then because the function is increasing, then if I use a value at the left endpoint, then automatically what this gives me is the smallest possible value of the approximation of the given interval. So from x1 to x2, what's the smallest possible approximation I can get is going to be an approximation based on the function value of the function on the left-hand interval. And so if I use left endpoint of an interval, so if I use left endpoints of each subinterval like in this picture, then that means that approximation of the area under the graph is going to be actually an underestimation, right? So if I'm adding all areas of these graphs below f of x equal to x squared, then I get underestimation of the area. And once again, how this underestimation will behave when I add up one more point. So when I'm taking the last subinterval, I'm splitting it into two. And if I'm using the right endpoint on each subinterval, nothing changes here. But down here, I'm going to raise the height of the rectangle, right? Because I'm using this right endpoint rather than this right endpoint. So the value is higher, and underestimation is better, right? It's not as bad as what it was before because this extra additional area that I need now has been reduced inside, right? Instead of a large rectangle, I have now two small rectangles and I saved this area. So then for a defined partition, underestimation, it appears to be that underestimation is going to become larger, right? So I have a regional partition, I refined it, I get an approximation which is better because it's a larger underestimation. Now that's what these superscripts mean. So here SO5 and SO6 are overestimations of Riemann sums overestimations of the area under the graph by using 5 rectangles and then 6 rectangles. And superscript U means underestimations. So if I define the partition, overestimations will decrease in size, underestimations will increase in size, so they will become closer to the actual value. And now again, if I think about underestimations, then what I can do is consider all possible underestimations of my area under the graph for a definite integral. And then if I take the largest of these possible underestimations, or if I take a supremum over this over any possible underestimation, then that supremum hopefully will be the value of the area itself, right? Because as I refine my partitions, I'm going to get better and better approximation, or better and better underestimation. And for underestimation to be better, that means that underestimation increases in size. So let's make a few rough points here. So point number 1. Each underestimation of the area, or overestimation first, each overestimation of the area is greater than the area itself. So that means that the set of all possible overestimations is bounded from below by the exact area. All right. And so then hopefully, infimum of all overestimations is going to be equal to the area under the graph. Right? So then in that sense, I would expect that the integral from 0 to a of x squared is equal to the infimum overall possible underestimations, or actually not overall possible underestimations, but infimum overall possible partitions P of partial sums as an overestimation that should depend on P. Okay? I can make a similar statement. Now, this is not a proof of anything. I'm simply trying to reason that I can use this approach possibly to deal with the definition of the integral. So what about underestimations? So each underestimation of the area is going to be what? Smaller than the actual area of the graph. And so that means that the set of all possible underestimations is bounded now not from below, but from above by the exact area. So, and then in this case, I should expect that the supremum overall possible underestimations will be the exact area under the graph. So I would expect then not the infimum, but the supremum overall p's of overestimations by using this partition. So I hope that this makes some sense, right? So we can try to then define the integral either as a supremum overall possible underestimations or infimum overall possible overestimations. All right, so something that we have seen already. If Q is a refinement of P, then if I compute as underestimation using partition Q, and if I'm computing underestimation using a partition P, then underestimation becomes better with refinement. So that means that underestimation of the area under the graph of my function by using a finer set of points should be closer to the actual value of the area, and because it's underestimation, the better underestimation should be greater or equal than the worse underestimation. And likewise, if I compare overestimations, SO of Q to overestimation using points from P, then overestimation, the better overestimation, is a smaller overestimation. So this should be true. As I'm refining a partition, overestimation goes down and underestimation goes up. Number 4, if I consider overestimation of the area using, let's say, partition P, and I consider underestimation of the area by using any partition Q, can I say anything about this? Well, any underestimation is less than the actual area under the graph. And any overestimation is greater than the area under the graph. So overestimation is greater or equal than the area. And area itself is greater or equal than as underestimation. So that means that it doesn't matter which partition P and Q I take as overestimation. Partition Riemann sum by using Riemann sum that we get by using for overestimations right endpoints is always going to be greater than another Riemann sum where you're using left endpoints. So this is then for any P and Q for any two partitions of interval from 0 to a. Okay, so then that is what we're going to try to do when we define the integral. We're going to try to work with these overestimations and underestimations. They have these nice properties that refinement will cause underestimation to go up and overestimation to go down. We'll use this property that any underestimation is always less than any other overestimation. We're going to use those somehow to prove that this statement that I put in number 1 here is going to be actually useful in a sense that if we take all possible overestimations and we take infimum of those, then that should give you the integral. And if I take underestimations and I take the supremums over all possible partitions of the interval, then I should get exactly the same number. So I can get the area under the graph as infimum over overestimations or as a supremum over underestimations. And so that is what I'm going to do in the next lectures. I'm going to introduce some terminology. And then once we introduce that terminology, we're going to go away from a specific example of x squared where things are more clear because the function is increasing. You can say that the largest overestimation is always, always going to get when you're using the right-hand point of the interval, and the largest underestimation you're going to get on a given interval by using the left-hand point. If a function is not monotone, that things are going to be slightly more complicated, but the basic idea is going to be precisely what I'm showing you here. That if I work with underestimations and overestimations, I might be able to get somewhere, right? Okay, and so we're going to continue with that in the next lecture.